Somewhere in Europe, engineers have drawn a line from Scotland to Norway, a wall meant to seal the North Sea. Another cut straight across the Strait of Gibraltar, an idea to drain the entire Mediterranean. In Egypt, there's a proposal to flood a desert the size of a small country, and near the Red Sea, one plan suggests pumping an entire ocean uphill. They sound impossible, but these projects are real, each backed by scientists, studies, and staggering numbers. And together, they share a single goal: to control the sea itself. The question is, could any of them actually work? In 2020, two oceanographers, Sjord Groskamp and Joachim Kjeldsen, proposed one of the most ambitious civil engineering projects ever conceived: sealing the entire North Sea with two giant dams. One stretching between Scotland and Norway, another between France and England. Together, they'd form a 637-kilometre wall holding back 570,000 square kilometres of water. But here's the catch: they never actually wanted to build it. The proposal was called NEED, the Northern European Enclosure Dam, and it was designed to protect 25 million people from rising seas, with a total cost of about €500 billion. But before we get to why this was meant as a warning rather than a solution, let's talk about the engineering challenge itself. The scale of this project is almost incomprehensible. The southern dam connecting France to England would be 161 kilometers long. That's significantly longer than any seawall ever built. The Saemangeum seawall in South Korea, currently the world's longest, is only 33 kilometers. The famous Afsluitdijk in the Netherlands is 32 kilometers. If you combined both of them, they'd still be less than half the length of Need South. And that's just the easy part. The northern dam would be 3 times longer, stretching 476 kilometres from Scotland, bouncing through the Orkney and Shetland Islands, all the way to Bergen on Norway's western coast. This section would cross the Norwegian Trench, where the ocean floor plunges to 321 metres deep. That's deeper than the Eiffel Tower is tall. No dam has ever been built at that depth. The deepest points of Need South stretch 102 metres, which is challenging but manageable. But 321 metres? That's in the territory of fixed oil rigs, which have very different engineering requirements entirely. Working at these depths means dealing with immense water pressure and complex construction techniques like caissons, giant concrete boxes filled with sand or gravel that can be dropped from boats and sunk to the ocean floor like colossal bricks. Now let's talk about materials. The entire structure would require 36 cubic kilometers of material. That's 100 times the volume of Afsluitdijk, the dam that took the Netherlands 5 years to complete in 1932. For another comparison, the Three Gorges Dam in China, the world's largest hydroelectric dam, used 27.4 million cubic meters of concrete. The North Sea enclosure would need over 1,000 times that volume. Groskamp's paper estimates the project would need more than 50 billion tons of sand. If you spread all that sand on the ground, you'd have enough to cover the entire United Kingdom. That sounds impossible, but here's the thing. 50 billion tons of sand are already collected every single year for construction projects worldwide. If sand production could be boosted by just 10%, it would take only a decade to stockpile enough for need. The construction timeline? At least 20 years. Though in interviews Groskamp admitted it could take closer to a century. So why even think about this? Because sea levels are rising fast. Since 1880, they've risen over 21 centimeters. By 2100, in the worst-case scenario, they could rise by 2 meters. Parts of the Netherlands are already below sea level. If the rise continues unchecked, up to 25 million people in low-lying cities like Amsterdam, Rotterdam, London, Copenhagen, Oslo, Stockholm, and St. Petersburg could face devastating flooding. The question becomes, is it cheaper to build a dam or move millions of people? Economically, the dam might actually be cheaper. Spread across 20 years of construction, the annual cost to the 15 countries involved would be only about 0.1% of their combined GDP. That suddenly sounds more reasonable, doesn't it? But Groskamp himself said this wasn't a real solution. It was a warning, because if NEED were built, it would break Europe. First, there's global trade. Rotterdam alone handles 7 million TEUs of containers annually. Hamburg processes 4.2 million TEUs. These ports, along with others like Antwerp and Bremerhaven, formed the backbone of Europe's economy. The English Channel, which lies entirely within the enclosed area, is the world's busiest waterway. If need were built, every single ship entering or leaving these ports would need to pass through giant sluice gates. Imagine the bottleneck. Long queues of vessels like you'd see at a commercial canal, waiting for hours to pass through locks. Shipping costs would skyrocket, delays would ripple through global supply chains, Europe's maritime economy would be crippled beyond repair. Second, the dam would need to pump water constantly. Rivers flowing into the North Sea combined with rainfall would create a discharge of 40,000 cubic meters per second. That's equivalent to emptying an Olympic swimming pool every 2 seconds. Grosskamp calculated this would require the energy output of just 9 of the world's largest offshore wind turbines running continuously. That part is feasible, but here's what isn't: the ecological collapse. Without the Atlantic's tides bringing in salt water, the North Sea would gradually turn into a brackish lake. Within 100 years, it could be 10 times less salty than today. The North Sea currently hosts over 200 fish species, including massive commercial fisheries of herring, cod, mackerel and haddock. Populations of whales and dolphins rely on these waters for food. Seabirds by the millions depend on the ecosystem. All of it would die. The fishing industry would collapse. Marine ecosystems that took millennia to evolve would be wiped out in a generation. The natural movement of currents, nutrients and sediment would stop entirely. And that's exactly the point. Grosskamp and Kjeldsen design need to protect against up to 20 meters of sea level rise, far beyond current projections. They made it deliberately extreme because they wanted to show the world what we'd be forced to build if we failed to address climate change now. In Grosskamp's own words, if we need to build it, basically, we failed. The dam's creators knew this was dystopian. They called it a warning from the future, not a solution. They wanted to demonstrate that the cost of inaction would force impossible choices, ruin ecosystems, cripple economies, or abandon millions to rising waters. So the real question isn't whether need can be built, it's whether we'll let things get so bad that we'd even consider it. 70 years before the North Sea Plan, a German architect named Hermann Sorgel had an even wilder idea. He wanted to drain the Mediterranean Sea, not partially, completely. His goal was to lower it by 200 meters. Sorgel was born in 1885 and lived through World War I. After watching Europe collapse into poverty and conflict, he imagined a grand fix, a project he called Atlantropa, blending Atlantic and Europa. His idea was simple in concept, but staggering in scale: unite Europe and Africa into one supercontinent by building a colossal dam across the Strait of Gibraltar. The strait is only 13 kilometers wide. You could almost run that distance, but it plunges nearly 900 meters deep. That's 3 times the height of the Eiffel Tower. For comparison, the world's tallest dam today, China's Jinping 1, stands 305 meters. Sorgel's barrier would have needed to reach triple that depth. And remember, this was 1927. The Hoover Dam, still a decade away, would top out at 221 meters. Sorgel was thinking 4 generations beyond his era's engineering limits. He knew the Mediterranean loses more water to evaporation than it gains from rivers, roughly 1,200 cubic kilometers every year, blocked the Atlantic inflow, and the sea would start to shrink. Over several decades, he calculated, the water level would fall by 200 meters, revealing more than 500,000 square kilometers of new land, roughly the size of France. Northern Italy would sprawl outward, the Adriatic would shrink into a lake, Greece, Tunisia, and Libya would all gain vast coastal plains. Even Venice would end up stranded on dry ground. Sorgel proposed 3 main dams. 1, the Gibraltar Dam, the centerpiece, controlling the exchange between the Atlantic and the Mediterranean. It would double as a hydroelectric plant, producing 110,000 megawatts of power, about 5 times more than the Three Gorges Dam produces today. 2, the Sicily-Tunisia Dam, a 150-kilometer barrier dividing the Mediterranean into 2 basins, the west lowered by 100 meters, the east by 200. Water cascading between them would generate even more electricity. Highways and rail lines would run across its crown, physically connecting Europe and Africa. 3, the Dardanelles Dam, sealing off the Black Sea to preserve its level. And beyond that, Sorgel dreamed of a Congo River Dam, forming a vast inland lake to irrigate the Sahara and green Africa. Canals would reconnect newly inland cities like Venice and Alexandria to the shrunken sea. For 25 years, from 1927 to 1952, he promoted this vision through books, lectures and films. He believed Atlantropa could end wars by giving Europe limitless land and energy, eliminating the fight over resources. But his timing was disastrous. The 1930s brought the rise of the Nazi Party. Sögel, a pacifist, used the term Lebensraum, living space, but for peace, not conquest. The Nazis dismissed him. They preferred faster ways to expand. Even without politics, the plan was impossible. Depth. At 900 meters, the Gibraltar Dam would face pressures of 90 atmospheres. Modern oil rigs can survive there vertically, but not as horizontal barriers holding back an ocean. It would have needed 1 to 2 cubic kilometers of concrete and rock, 40 to 80 times the volume of the Three Gorges Dam. Seismic risk. Gibraltar sits on the boundary between the African and Eurasian plates, a highly active fault zone. If the dam ever ruptured, the Atlantic would surge back in exactly as it did 5.3 million years ago during the Zanclean flood, when waterfalls nearly a mile high refilled the Mediterranean in months. A repeat would obliterate every new settlement. Economics. Lowering the sea would strand every major port: Barcelona, Marseille, Genoa, Naples, Athens, Alexandria, Tunis. Rebuilding them all would cost trillions. Centuries of maritime trade would vanish overnight. Modern construction would still need 50 to 75 years. The Gibraltar Dam alone might cost $150 to $250 billion. The Sicily-Tunisia barrier could approach $1 trillion. Add port reconstruction and power grids, and the total climbs towards $5 trillion. Yes, the energy output could reach 110 megawatts, theoretically worth $48 billion per year, but that assumes flawless operation and perfect political cooperation among 15 countries. Even Spain and Morocco can't agree on a simple tunnel across the strait. Not to mention the environment. The Mediterranean is home to 17,000 species, 7,000 found nowhere else. Seal the strait, and salinity and temperature would shift beyond survival limits. The sea would suffocate, and its fisheries would collapse. Sögel died in 1952, hit by a car while cycling. He never saw his vision realized. In the end, Atlantropa failed for the same reason the North Sea enclosure will never be built. The cure was worse than the disease. But nearly 100 years later, a new kind of ambition emerged. This time it wasn't architects chasing utopia. It was scientists asking a terrifying question. What if the only way to save the planet is to destroy part of it? Some ideas are never meant to be built. They exist to make us think about what's possible, what's right, and what's too far. The Red Sea Dam is one of them. In 2007, geologist Roelof Dirk Schulling and his colleagues at Utrecht University published what might be the most provocative engineering proposal ever written. A plan to dam the Red Sea at the Bab el-Mandeb Strait, where it meets the Indian Ocean. The strait is only 29 kilometers wide. You could drive that distance in 20 minutes. It sounds almost manageable, until you hear the numbers. They proposed a dam 150 meters high, 1 kilometer thick, and 100 kilometers long, stretching between Yemen and either Eritrea or Djibouti. Taller than the Statue of Liberty, thicker than 10 city blocks of concrete. The mechanism was deceptively simple. The Red Sea evaporates faster than any river can refill it, about 2.1 meters per year. Right now, the Indian Ocean flows in through Bab el-Mandeb to keep the level stable. Block that flow, and the Red Sea begins to shrink. As its level drops, seawater would be pumped back through turbines, generating power from the fall. The result? 50 gigawatts of clean energy. That's as much as 50 nuclear plants, or 15 times the output of the largest nuclear facility in the US. It would be the biggest renewable energy source on Earth. But here's where it gets absurd. The dam wouldn't produce power for 50 years, until the sea had fallen 100 meters. At that point, it would only generate about 19 gigawatts. Reaching the full 50 gigawatts would take 291 years as the sea dropped 611 meters. Construction would start in 2025, first power in 2075, full capacity in 2316. For comparison, the Three Gorges Dam in China, the largest hydroelectric plant on Earth, produces 22.5 gigawatts. It cost $31 billion, took 17 years to build, and reached full capacity in less than a decade. The Red Sea Dam would take 17 times longer just to start generating power, and almost 3 centuries to reach its peak. The cost? Between 100 and 200 billion euro for the main structure, plus 15 to 20 billion euro for a secondary dam near the Gulf of Suez. 6 times the price of Three Gorges for results that wouldn't arrive for generations. Not to mention the environment. The Red Sea is home to 1,200 species of fish and some of the planet's most resilient coral reefs, ecosystems surviving in water temperatures that would kill coral anywhere else. Seal the strait, and salinity would spike while oxygen plummets. Within years, the reefs, mangroves, and coastal wetlands would collapse. Fishing would vanish, tourism would die, and cutting off 450,000 square kilometers of ocean would even raise global sea levels by 12 centimeters, about 20 years of climate-driven rise. Environmental advocates call it ludicrous. Peter Boshard of International Rivers compared it to the Soviet disaster of draining the Aral Sea. He asked, "Is this serious or a parody of obsolete macroengineering?" But the scientists weren't joking. They acknowledged the destruction outright. Macroengineering projects of this size cause massive destruction of existing ecologies. Their paper framed the dam as an ethical question, not a construction plan. Is it ever acceptable to destroy one ecosystem to save another? Now imagine another idea, one that doesn't create power at all. The Bering Strait separates Alaska and Russia, connecting the Pacific and Arctic Oceans. Every year, warm Pacific water flows north through this channel, helping drive the global current system known as the AMOC, the Atlantic Meridional Overturning Circulation, which keeps Europe's climate stable. But that circulation is slowing. Melting Arctic ice is dumping fresh water into the North Atlantic, diluting salt and disrupting the system. If the AMOC collapses, Europe could plunge into a new climate regime. Some researchers have suggested blocking the Bering Strait to limit the freshwater flow, a geoengineering shortcut to stabilize the planet's currents. In theory, it could work. In practice, it's a planet-scale gamble. If built too late, after the AMOC is already weak, the dam could do the opposite, accelerating the collapse and heating the Arctic by several degrees. And once built, you can't undo it. The politics are just as impossible. The strait lies between the United States and Russia, two rivals who barely cooperate in peacetime. It's also a vital shipping lane and a migration route for Arctic wildlife and indigenous communities who depend on it. Like the Red Sea Dam, this isn't a plan, it's a warning. Both proposals are scientifically grounded enough to be plausible, yet extreme enough to show the cost of desperation. Not every plan to reshape the planet involved building walls across oceans. Some tried the opposite, bringing the sea inland. And few went further than Egypt's Qattara Depression project, a plan to flood a desert basin the size of Connecticut and turn it into a vast artificial sea. About 60 kilometers south of Egypt's Mediterranean coast lies the Qattara Depression, one of Africa's lowest points, 133 meters below sea level. For almost a century, engineers have looked at this dry bowl and imagined using it as nature's hydroelectric dam. The concept sounds simple: cut a canal from the Mediterranean to the depression, let seawater flow downhill. As it cascades into the basin, it spins turbines to generate electricity, then evaporates under the desert sun. The balance between inflow and evaporation would keep the new lake's level stable, producing a continuous source of power. At full scale, the Qattara project could have generated 5.8 gigawatts, almost 3 times the output of the Aswan High Dam. The idea first appeared in the 1920s, but it gained real momentum in the 1950s and 60s as Egypt's population soared and demand for electricity exploded. The project's appeal was obvious. Unlike Aswan, it didn't rely on the Nile. It turned geography itself into a power source. In 1957, the plan even reached Washington. Declassified CIA memos show that American officials proposed it to President Eisenhower as a way to win over Egyptian leader Gamal Abdel Nasser during the Cold War. By the 1970s, German engineer Friedrich Bassler revived the project with a detailed 3-phase proposal. Phase 1 would build a 670-megawatt pilot plant called Qattara 1. Phase 2 would add 1.2 gigawatts of conventional hydro stations, and Phase 3 would complete the vision, a 4-gigawatt pumped storage facility using a high-level reservoir capable of holding 50 million cubic meters of water. During low-demand hours, water would be pumped uphill. During peak demand, it would be released, effectively turning the desert into a giant battery. According to Bassler's calculations, the depression would fill to approximately 60 meters in roughly 10 years, covering an area of 12,000 square kilometers, a lake stretching nearly the width of Lebanon. Keeping that level steady would require a constant inflow of 600 cubic meters per second, compensating for 19 billion cubic meters of annual evaporation. The canal itself would be a mega-project in its own right, 60 meters deep and 60 to 100 kilometers long, potentially navigable for shipping, complete with harbor and fishing facilities inside the new inland sea. But the question was how to dig it. Bassler's solution sounds unthinkable today. Use 213 nuclear bombs to blast the canal through solid limestone. Each device would yield 1.5 megatons, roughly 100 times the Hiroshima bomb. He argued it was the only way to move that much rock economically. But the risks were staggering. At least 25,000 people would need evacuation, radioactive fallout could contaminate the air and groundwater, and the shockwaves might destabilize the Red Sea Rift, 450 kilometers away. Even if nuclear excavation worked, another danger lay hidden beneath the sand: landmines. During World War II, the Battle of El Alamein turned the Qattara region into one of the world's largest minefields. Hundreds of thousands of unexploded mines remain buried there to this day. Clearing them would take years and millions of dollars before a single bulldozer could move. Combined with the project's multi-billion-dollar cost estimates and global opposition to peaceful nuclear explosions, Egypt quietly shelved the plan. While Egypt dreamed of bringing seawater to the desert, another part of the Middle East faced the opposite problem: a sea that was disappearing. The Dead Sea is shrinking faster than any other large body of water on Earth, dropping more than a meter each year. In 6 decades, it has fallen over 30 meters, leaving marinas stranded far from the shore. The reason is simple. The Jordan River, once delivering 1.3 billion cubic meters of water annually, now sends less than 100 million. Most of its flow is diverted for irrigation and drinking water. As the sea retreats, the ground collapses, sinkholes open, and resorts close. In response, Israel, Jordan, and the Palestinian Authority signed a historic deal in 2013, the Red Sea Dead Sea Conveyance Project, a 200-kilometer pipeline across Jordan designed to pump seawater from Akbar on the Red Sea to refill the Dead Sea. The plan had 3 goals: stop the Dead Sea's decline, supply drinking water through large-scale desalination, and promote regional cooperation. It was backed by the World Bank with a price tag of around $10 billion and expected to take 10 to 15 years to complete. The engineering challenge was extraordinary. The Dead Sea lies 430 meters below sea level, making it the lowest point on Earth. That meant the project would need to pump seawater uphill by nearly half a kilometer before it could flow down to the Dead Sea. Dozens of pumping stations spaced every 20 to 30 kilometers would push water through the desert, powered by an enormous energy supply network. Maintenance roads and security corridors would shadow the entire route. At Akbar, a new desalination plant would produce fresh water for Jordanian and Israeli cities, while the leftover brine, roughly equal in volume, would be sent north to replenish the Dead Sea. If it worked, the system could produce hundreds of millions of cubic meters of fresh water each year while stabilizing the Dead Sea's level. But scientists warned of hidden risks. Mixing the Red Sea's warm, salty water with the Dead Sea's dense mineral brine could trigger unexpected chemical reactions, forming gypsum crystals that would turn the surface milky white and devastate the area's tourism and potash industries. Marine biologists also raised concerns that siphoning water from the Gulf of Akbar could disrupt local coral ecosystems and alter current patterns in one of the Red Sea's most delicate marine zones. Politically, the project faced even greater obstacles. By 2021, Jordan formally cancelled the project, citing high costs and political strain. The Dead Sea continues to shrink, a reminder that even well-intentioned megaprojects can drown in politics before they ever touch the water. Across a century of ideas, from sealing seas to draining them, from flooding deserts to pumping oceans uphill, one thing never changed: humanity's need to control the water that defines our world. Every one of these projects, from the North Sea to the Dead Sea, tried to bend nature to our will, and every one of them ended the same way, as a warning. Because in the end, these aren't blueprints for the future. If you enjoyed this MegaBuilds story, leave a comment and tell us which of these projects you think could ever work, or which one should never be attempted. And if you want to see more deep dives into the world's most ambitious megaprojects, make sure to subscribe and hit the notification button. There's a lot more to come.